If you want to store information perfectly, the easiest way is to keep it all on a single machine. When one server handles every incoming request in strict order, the data is completely reliable. But modern applications process billions of actions. A single server will quickly collapse under that volume. To handle the load, engineers have to split the database across hundreds of separate machines. When you distribute a system, you introduce the problem of simultaneous action. If two conflicting requests, like a buy and sell order for the same stock, hit different servers at the exact millisecond, the database must figure out which happened first. Many databases settle for eventual consistency. They accept the chaos, allowing users to briefly see conflicting information before the system eventually syncs up. But for critical financial transactions or secure user records, the system requires strong consistency. The data must be perfectly accurate at all times. Perfect order across hundreds of machines doesn't happen naturally. It requires an active, mathematically rigid set of rules to force agreement out of digital chaos. When a user hits submit, the request hits a load balancer. Before it can move deeper into the network, it needs a permanent, unique identity. This diagram breaks down assigning identity. The sequencer stamps incoming requests with a 16-byte code, combining a nanosecond timestamp with the server's unique ID. This solves simultaneous writes. If two inputs arrive at once, the system enforces last write wins, comparing the 16-byte stamps and accepting the highest number. With its identity set, the data needs a destination. A component called the metadata manager acts as a global map. It reads the request and routes the data to a specific territory, a replication group of servers that handles that exact portion of the database. Timestamps create an order of events, and the map provides a destination. But routing a packet to a server does not guarantee it has been safely written to memory. Inside a replication group, 3 to 5 interconnected nodes hold the exact same data. To maintain consistency, the system elects one node as leader. It acts as the absolute gatekeeper. Every read and write passes through it. Receiving a write request, the leader cannot act alone. It immediately pushes copies down to secondary followers. The system waits. It will only confirm a successful save to the user after a strict mathematical majority of these nodes successfully write the data to their physical hard drives. Truth in this architecture isn't dictated by the memory of a single machine. It must be agreed upon by a mandatory quorum. Servers crash and cables fail. Consider what happens if the internal network fractures, severing the current leader from the rest of the group. The metadata manager immediately detects the silence. To keep the system alive, it evaluates the remaining connected nodes and elects a new leader. This diagram illustrates the split-brain paradox. The isolated old leader runs completely unaware it's replaced, while the new leader takes command. If a delayed request hits the false old leader, it attempts to process it. But followers only recognize the new leader, so the old leader's request is categorically rejected. Because every action requires a majority quorum, a fractured network mathematically cannot corrupt the database with unauthorized writes. Over time, individual sections of a database, like a table tracking billions of stock prices, grow too large and process too many inputs for a single replication group to handle. The control plane splits the hot table, migrating the new half to a different replication group. During migration, the system executes a dual read, querying both groups simultaneously. By checking their 16-byte sequence numbers, it mathematically proves the most recent version, returning the correct data. Even while tearing itself apart to migrate records across servers, the strict adherence to quorums and timestamps guarantees no data is lost or misread. When operating at scale, thousands of nodes coordinate millions of simultaneous reads and writes in a massive, unified rhythm. But engineering a system to guarantee absolute accuracy carries an explicit cost: the time it takes to recover from a failure. If a leader node dies, the entire replication group pauses. It takes roughly 1 second to safely elect a new leader. For that single second, that specific portion of the database is completely unavailable. That brief outage is an intentional design choice. The system prioritizes perfect data integrity over continuous uptime. In distributed engineering, there are no perfect solutions. By willingly trading a moment of availability,
This architecture secures an ironclad guarantee of the truth.